the lecture from last time. For the purpose of today's lecture, let us recall that we are considering a Navier-Stokes system in a corrugated pipe. So we are considering a three-dimensional physically realistic setting. We are interested in detecting both the effects of roughness and the effects of inertia on the effective flow. The boundary conditions are in line with the applications, so we assume that the flow is governed by the prescribed pressure drop, while on the corrugated boundary we prescribe classical no-slip boundary condition for the velocity. The idea is to seek the solution in a Poisson-like form. So you do not have to write this. I will just write that essentially the idea is to consider zero-order approximation in the following form. This is all from the last time. So this is bold. So this part is classical Poisson solution, which can be obtained directly from the governing system by considering the setting without roughness, so putting that shape function equal to 0, and we correct it by this term here, which we expand in powers of the small parameter standing for the average boundary roughness parameter. And then the key thing is to observe that we cannot meet no-slip boundary condition on the corrugated boundary because it depends on the longitudinal variable. And the idea is to impose that on the corrugated boundary, so on the upper boundary, we cannot simply put this equal to 0. That cannot be satisfied due to this longitudinal variable, but we impose this condition. And therefore, the Poisson solution has to be corrected by adding the corresponding boundary layer corrector. So we seek for the velocity in the following form. So this guy here plus boundary layer correctors. And of course, for the pressure, we have this all has been done on the last lecture. Pressure, this zero-order approximation for the pressure was a simple linear function with respect to the longitudinal variable. Okay. And now the idea is to put this into the governing system, which has been written in cylindrical coordinates, which has been written in dimensionless form. So we have explicit Reynolds number in the equations, and to consider this boundary condition. By doing that, at each step we obtain problems satisfied by the boundary layer correctors. Last time we showed how to deal with the problem satisfied by the first boundary layer corrector, B1. We emphasized the main theoretical results that we use to confirm the well-posedness of the corresponding boundary value problems and exponential decay as well. The idea is that we have these constants that can be chosen in a way that our boundary layer corrector vanishes outside the boundary layer. So if you recall from the last lecture, for instance, for B1, we obtained something like this. This W is the solution of the first one of the among many auxiliary problems, and the idea is to choose this guy here such that this boundary layer corrector exponentially decay towards 0 as the fast variable as the fast variable tau goes to minus infinity. So originally it decays towards a constant, and now since we have the liberty to choose this constant in this expansion here, we choose it in a way that this guy here exponentially vanishes. So by putting this, where this is a stabilizing constant of this auxiliary value problem, we achieve that this holds here. And this is the only non-zero component that we have from the exponential. The other component equals to 0 immediately, but this originally is a constant, and by choosing K1 in this manner, we fulfill this, and that is what we want to do. We do not want that our boundary layer correctors spoils our approximation outside the boundary layer. And now we continue this process, as I mentioned last time, and deduce the problem for B2, deduce so these are all bold, yeah? Deduce the problem for B3. We have to deduce, I think, even the problem for B4. Yes. Why is that? Because we want to capture the inertia effects as well. So the Reynolds number in the inertia terms for the first time appear. No, they appear for B3, but in order to get more accurate approximation, we even consider the problem for the boundary layer corrector B4. Of course, I'm not going to write all that here, because it gets messy with a lot of terms, but the idea is the same. The results, theoretical results that we apply is the same, and at each stage we choose these constants in a way that these guys here exponentially decay towards 0. The good thing is that we can compute these constants. For instance, here, this W infinity that was the stabilizing constant for the first auxiliary problem can be computed in this way. And now for B2, we will obtain the second auxiliary problem. For B3, we will obtain, to solve the problem for B3, we will have to impose 2 auxiliary problems, but they are all more or less of the types that we can treat by using previously derived results. Okay, so I will skip this part. You can look at it in the paper, and I will now just write the velocity approximation. So in each step we obtain K1, K2, K3, K4, which means that our velocity approximation takes the following form. So this is new. This was the recapitulation of the last lecture. So velocity approximation So our velocity approximation is in fact this one. So I will denote it by this. Okay, I will write all this. So it is essentially this guy here, which I will denote by this. So this is this one, y4 here, because we compute this k up to the fourth term, plus the boundary layer correctors. And we also go so this is our velocity approximation. Okay, let us write this guy here. This guy here is so the Poisson solution corrected by k epsilon. So k1 epsilon, k2 epsilon, k3 epsilon, k3, and this one, of course, in the longitudinal direction. So from now on, we only write the longitudinal components, since it is obvious that the radial one is of no interest here. Okay, so the longitudinal component, which we denote like this is essentially, sorry, is this one. So when we put this here and collect the terms with equal power of epsilon, we obtain the approximation, the longitudinal component of the approximation in the following form. Okay? Now I can erase this. And if you recall the very beginning of the last lecture, the ultimate goal here is to correct the well-known Darcy-Weisbach law. So we have to go back to dimensional setting, okay? So in dimensional setting, so going back to dimensional setting, our velocity approximation takes the following form. In this expression here, I will acknowledge the expressions that we obtain for these constants k1. Okay, so k1 is this, k2, k3, and k4. I did not write them, but you can look at it in the paper. So in dimensional setting, our velocity approximation take this final form. This was the mean velocity, if you recall, obtained. This was the characteristic velocity taken to be mean velocity of the standard Hagen-Poisson velocity. Okay, now see here, this is K1, so this is this term here. We go back to dimensional setting. So K1 was chosen to be this stabilizing constant. Now for K2, we obtain something else that is linked to a new auxiliary problems and correspondingly to new stabilizing constants. So see this is this guy here, okay? So to solve the problem for the boundary layer corrector B2, we have to introduce auxiliary problem that is of course different from this auxiliary problem satisfied by the W. We denote it by M, and this is the stabilizing constant that results from this auxiliary problem. For the third term, we have two auxiliary problems. And here, for the first time, we obtain the Reynolds number. In other words, inertia effects. Okay, what do we have here? So this is this term here. To solve the boundary layer, the boundary problem for the boundary layer corrector B3, we have to introduce two two auxiliary problems, because we get in the problem satisfied by this boundary layer corrector, the inertia terms also appear, and these are the corresponding stabilizing constants. This K3, this K2, as well as K1 are chosen in a way that boundary layer correctors exponentially decays towards zero. And finally, the last one. So, two more auxiliary problems. The first one is denoted by N41, and the second one corresponding to inertia terms. And that is that. Okay, so let us look at this approximation that we obtained. So this is the standard Hagen-Poisson velocity. So this here represents the higher order correction of the standard Poisson velocity. It obviously feels the effects, the roughness-induced effects, because the small parameter epsilon essentially denotes the average boundary roughness. And also, we are in position to compute the stabilizing constants that also feel the effects of the roughness, because they contain the shape function h. The effects of inertia are can be observed here. So our higher order approximation feels both the roughness-induced effects and the effects of inertia. It obviously depends on these stabilizing constants that can be all numerically. Some of them can be analytically expressed in the form of the integrals, but they all can be numerically deduced from the auxiliary problems satisfied by the they can be all solved numerically from the auxiliary from the corresponding auxiliary problem. And so this is the first part. So we obtain the velocity approximation. Now we want to see how it affects the Darcy-Weisbach law. So the idea is to put instead of just considering the Hagen-Poisson velocity and taking its mean value, now to consider this higher order approximation that is without any doubt more accurate, put it in the Darcy-Weisbach law and deduce the friction coefficient. Okay, so now, and that is essentially the result that enabled us to publish this result in engineering, one of the leading engineering journals. So, like a subtitle, Darcy, Weisbach, friction coefficient. Of course, maybe a few words should be said about rigorous justification of this approximation. So our analysis was the formal one. So we assume the ansatz, we assume the expansion, and we solve the corresponding boundary value problems. However, you should observe that in constructing the boundary layer correctors, we did not take into account the conditions on the pipe's ends. So in order to the possible way to provide rigorous justification is to from the starters to impose the periodicity condition on the pipe's ends, but this is not with respect to the longitudinal variable, but this is not in line with the application. So with rigorous justification, we should either replace either impose periodicity condition with respect to the longitudinal variable, or deal with another boundary layer that will appear in the vicinity of pipe's ends, and that is rather complicated, and it is not sure that we would be able to do that. But for us here, we have another paper that was published in Matematička journal with rigorous justification. Here, that was not the goal. Goal here was to treat the physically relevant situation, so three-dimensional setting, to put pressures at pipes, impose pressures at pipes ends, and to do this, to show that our higher order approximation actually in some way corrects the usual friction coefficient used throughout the engineering literature. So, Darcy-Weisbach formula, I wrote it last time at the beginning of this lecture. So in our case, it reads something like this. So this was the friction coefficient. And now instead of the mean velocity, here we put our mean velocity. That will be computed from this expression here. So we denote it like this. So this did we have some labels last time? What was the last one? I want to denote this by something. 6. So this would be 6 or 7? This would be 7. 7, okay. Okay, so for the purpose of our analysis, let us first compute the friction. So this is the friction coefficient, okay? So let us first compute this FD for the case of the pipe without roughness, okay? So the usual formula that engineers use. So for age equal to 0 and V equal, let us recall this formula. So for age equal to 0, this mean velocity is essentially the mean velocity of the standard Poisson velocity, and it takes the following form that we did last time. Okay. So now we obtain something like this. So putting this into the here, okay, putting this here, we obtain because we know that Reynolds number is this. So we put this here, okay, and notice the Reynolds number, and we obtain something like this. And then we obtain that in case of the pipe without roughness, so standard smooth pipe, we have this friction coefficient. This is important because what do we want? We want essentially, okay, so from the physics we know that the pressure loss should be affected by the boundary roughness, okay? So now the idea is to use our higher order approximation, put it here, and deduce this guy here. So this will be corrected by some terms, okay? And this is our, we believe, more accurate Darcy-Weisbach friction coefficient for the corrugated pipe. In order to do so, we have to compute the mean value of this. So let us denote our domain by omega epsilon. So now we are back to yes, now we are back to non-dimensional case. Well, I should skip this. Okay, I will start so you can understand. So we denote this our domain after non-dimensionalization. We compute this. Okay, I will not write this. Oh, okay, I will. So it's why we need this? Because I will have to erase this, unfortunately. Okay, now we compute the mean velocity up to an order epsilon to the fourth. So we denote it like this. Only the longitudinal component. Okay, and now if you recall the formula for this guy here, it contains a lot of terms and a lot of integrals should be computed, but that can be done that can be done, and after a lot of computation, we obtain something like this. So 1 over this term here, okay, I will write here also. So and here we have something like this. So this A epsilon is something like this. I will not write all these constants, but they can all be computed via some integrals. And this K epsilon is also in something like this. So these constants A1 to A4, K1, K2 can be computed by taking into account the expression that we obtain for this non-dimensional velocity approximation. Okay, so this is our velocity, mean velocity, but in non-dimensional setting. So we have to go to dimensional setting. So we denote, so in dimensional form, we introduce this kind of notation. It is essentially the characteristic velocity times this non-dimensional velocity, where the characteristic velocity was written here as the mean value of the Hagen-Poisson velocity. And now we put this here. Okay? And after doing that, and now we will replace this one by capital FD, because we will here obtain a different formula for this friction coefficient. So putting into Darcy Weisbach Law 8, and this should be labeled 8. We obtain this, and replacing FD by capital FD, we obtain the following. And now from this expression, we deduce the friction coefficient. Okay? and we deduce the Reynolds number from here. So we obtain something like this. And this is the formula that we propose as the correction of the friction coefficient due to the roughness and the inertia as well. So if you compare this with this, then here you have this FD, small fd, that is obtained for smooth pipe, so without roughness. Okay? And obviously, this FD is corrected by this term here. Okay, and now we can deduce the following. So now I will erase this and write the concluding remarks. So from 9, we deduce the following. First, if Reynolds number is not too large, so we have is not too large, so we have a slow flow. Then, so this is small. Then this guy here obviously dominates this one here. So term dominates this one here. So we can now do some calculations for this correction of the friction coefficient obtained for the case without roughness. So if we assume that this dominates over this, then this behaves as the following. Of course, here, recall, so this A epsilon was this. We neglect these terms because the average boundary roughness is small, so we just put this, okay? And we computed all, as I said before, all of these constants are computed via the stabilizing constants from the auxiliary problems. And if we take into account the expression for the A1, we obtain something like this. And if you recall, this guy here was computed as minus something like this, yeah? Okay? And it's obviously negative, okay? So this is positive, we have 1 plus something negative, so this guy here is obviously greater than 1. So what is the conclusion? So we obtain that this multiplying factor that corrects the friction coefficient is greater than 1. That leads to a conclusion that the pipe's roughness essentially increases the friction coefficient, and that is to be expected, okay? So the conclusion here is that pipe's roughness, and that we conclude from the formula 9, so pipe roughness increases the Darcy-Weisbach friction coefficient. And that is expected if you think a little bit from the physical point of view. The second conclusion is the following. I will erase this and leave the friction coefficient. So this was the first one. The second conclusion, if the magnitude of Reynolds number is significant, and we are still significant, and we still remain in a laminar regime, then this guy here should not be negligible with respect to this one. And friction coefficient should be computed, maybe here is not negligible, should be computed from formula 9. Okay? And these are our main contributions from the engineering point of view. So we derived analytically the correction of the Darcy-Weisbach law, okay? For the case of the rough pipe. And now since when you start some investigation and make first results, then it is always wise to use this approach on different models. So not just remain on starting viscous flow. So the idea always is to extend the approach that you developed to different regimes, to different settings, and publish all those results because they can be interested from for many readers. So possible applications. In this case goes to considering to extending the situation from here to a porous medium flow. So like some subtitle, application to porous medium flow. So here I'm going to present some basic models which are considered when treating porous medium flow. That means that the pipe or the channel is filled with some porous medium. And why we can all most likely extend the analysis from the situation without porous media inside the channel or the pipe, because there are very good models. They do not are of the same type as the Navier-Stokes equations that essentially describe the porous medium flow. The first so we always have the incompressibility equation. It always remains in the system, coming from the conservation of mass. Here, U is the filtration velocity. So the velocity of the fluid going from the porous medium. So this is from the conservation of mass. However, different laws have been used for the conservation of the linear momentum. The first, the most basic, the most famous one is the Darcy law, okay? So to describe the momentum, the conservation of the linear momentum, we can use either Darcy law, which is the most simple one, so here P is the pressure, K is the permeability of the porous medium. So P pressure, K permeability, and me, of course, viscosity coefficient. So this is the Darcy law. I believe that you all are familiar with it. It is the most simple one, but it cannot take into account the no-slip boundary condition imposed on the impermeable boundary of the considered domain, and that is its main drawback. Then Brickman, so this is Darcy law from what year? Okay, now we can either consider this. We can consider the so-called Darcy Brickman equation, which is of the second order, and thus it can acknowledge the no-slip boundary condition, which, so it's this one. Here we have the effective viscosity that should not be equal to this viscosity of the fluid. And for the purpose of our analysis, we prefer this system over this, because it's, if you neglect this one, that's essentially the Stokes system, yeah? So we have this linear term here that does not cause many problems. So this is the Darcy Brickman law, or Darcy Brickman equation. Brickman equation, proposed by Brickman in 1947. Here we have this effective viscosity, which I repeat does not have to be viscosity equal to the fluid's dynamic viscosity. So this is effective viscosity of the fluid in the porous medium. And this system, so this equation together with continuity equation, is for the purpose of the analysis better. And from the physical point of view also, because since this is a second order equation, we can impose the no-slip boundary condition on the impermeable boundary of the considered domain. And it turns out that in case of the fluid saturated sparsely packed porous medium, this Brickman extension of the Darcy law is the most suitable one. However, you can see here that inertia effects are neglected. So if one wants to consider the inertia effects as well in the porous medium flow, then the momentum equation can be considered as the following. See. So without this, we have a Darcy Brickman equation. Now we have a nonlinear term. Here, this rho is density of the fluid, and this phi is porosity. But the important thing is that now this so-called Darcy-Lapwood-Brickmans equation from 1948, obviously proposed by Lapwood, is the one to be considered if we consider flow through a fluid saturated, sparsely packed porous medium, and do not want to neglect the inertia terms. So for moderate Reynolds number. And so we have this equation together with this equation. If we compare this system, so let us denote this by 10, and this one by, oh, sorry. So please put something like this, put dots, please. So this, okay? And denote this by 11. So if we now observe the system 10, 11, what is new compared to another Stokes system that we treated so far? The new is this term here. And this term here is linear. And we can deal with it, okay? Now the idea is to extend the analysis that I did last time and this time to this system here, okay? So the idea, extend the analysis to system ten, 11, okay? And that has been done in a case of two-dimensional channel in my paper joint with Edward, published also this 2020 in a journal Transport in Porous Media, which is one of the leading journals for porous media flows. This engineering community dealing with porous medium flow is very large. And I must say, from the mathematical point of view, main contributions to porous medium flows are due to our Andro Mikelic. Okay, and I will finish with that today. See you next Thursday. Next Thursday we are going to address a different problem. So we are going to address a flow through a domain with a porous boundary. So we want, starting from the original equation and describing, for instance, the lower porous boundary, we want to derive the effective boundary condition on this porous part of the boundary. Okay, thank you very much. Do you have some questions? No, this was, no. I assume that it can be, No, I have never think about that, but yeah. But I think that it gets very messy because you have a coupled system, and the boundary, those auxiliary problems, even for the Navier-Stokes equations, are very complicated. So but for some kind of PhD dissertation, maybe, I don't know. It will get very messy. Because here I skipped this messy part. The analysis for B2, B3, B4, And if you add equation for the micro-rotation, I think that it can be done, but it requires a lot of work. I also did the extension to a hydrodynamic flow. Yeah, so I put, let me recall, was it porous media or Yeah, through porous media. If you add here another term coming from the effects of the electric field, then also it can be done. This analysis also can be done because it's again a linear term, and you can done. But if you want to treat micropolar system, then you have more equations, and I will not do it. If you want it, please do. Okay. See you next Thursday. Thank you very much.